G'day again. Welcome back to Mathematics 302. Hope you're having a good morning. Hope you had a nice coffee or hot chocolate or something to stay warm. I've got my earmuffs on today. It's a little bit chilly, or tonight. Just move the image down. This is lecture 2 and part B. So let's get into it. Okay, so we're going to do injection, surjection, and bioinjection. Just a really quick single frame reminder. Then I'm going to do Cantor's theorem, the Barber paradox, and Cantor's diagonal argument, which is all connected to Cantor's theorem, and the Schroeder-Bernstein theorem. There's not a lot of questions that can be asked about all of this. So I'm actually going to give you a question that will be in the first assessment test. Just so you don't arrive in the test and go, oh my goodness, how am I going to answer this? Okay, so this is just a reminder. Hopefully you've seen this before, maybe in second year in that lecture. So this is just a reminder, injective. So injective is where you've got one set going to another set where everything in, like if this is set A, everything in set A goes to something in set B. And you notice here, this one's left off. Not everything in set B is covered. That just means that everything from set A is going into set B. That's called a one-to-one relationship, even though it's not fully, completely one-to-one. They regard injective as one-to-one because it's one to one thing in B, regardless of whether there's things missing in B that don't get one-to-one. Okay, surjective is where you've got all of these elements in A going to something in B, but two things may go to the same thing. So that's surjective, and that's regarded as onto. So in other words, everything in A is placed, and everything in B has something, even if B has more than one thing. Then you've got bijective, and bijective is where everything is literally one-to-one, which is possibly a bit confusing here, and they regard that as one-to-one and onto. Okay, so that's just a reminder of how things are viewed in terms of set and the wording that they typically use. Okay, Cantor's theorem. This is quite interesting, and hopefully you'll appreciate the interest in this, especially when I give you the question. Okay, for any set, the cardinality of its power set, the set of all its subsets, is strictly greater than the cardinality of the original set itself. So if A is a set, then the absolute value of A is less than or equal to the absolute value of the power set of A. So really simple proof for the finite version of Cantor's theorem. This is not necessarily something you would get, but it is an acceptable way to do a proof. There's other ways. So let A to be a finite set and let PA be the power set. So A, absolute A, is less than or equal to absolute PA. So we want to prove that. So since PA, the absolute value of PA is 2 to the power of A, or to the absolute power of A, we're going to do it by a typical high school proof. So let the absolute value of A equal K. So by induction, we're going to assume K is less than 2K for any positive integer K, and I've just marked that with a big hash. I did have a star there, but the star kept being up here. I couldn't quite get the star to be in line, so I've just called it a hash. So I'm going to refer back to that in a typical induction way. So we're going to show that K plus 1 is less than 2 to the K plus 1 is true. In other words, we've just added 1 to the K there. So we're going to multiply hash, which is this one, by 2. So then we get 2 multiplied by K is less than 2 multiplied by 2 to the K. And obviously now our next move, this 2 is going to come up here and be K plus 1. So now 2 times K is less than 2 to the K plus 1, just moving that as a power, making that fairly obvious. So now we've got 2K is less than 2K plus 1. We've also got K plus 1 is less than 2 to the K plus 1. So what we're going to now say is that K plus 1 is less than 2K. And that's pretty obvious because we're just using integers. K is just increasing 1, 2. So if K was 1, 1 plus 1 is 2. 2 times 1 is 2. So it's equal. If K is 2, 2 plus 1 is 3. 2 times 2 is 4, so 3 is less than 4, etc., etc., etc. So these are just positive integers, and for everything else, this is going to be true. Therefore, we can say k plus 1 is less than or equal to 2k, and that is less than 2 to the power of k plus 1. So therefore, k plus 1 is less than 2 to the k plus 1. So we've proved Cantor's theorem for a finite set. Okay, so here's Cantor's theorem, an example, and I'm pretty sure I did this in the previous lecture, in lecture 1. So let A be 1, 2, 3. So the power set is the empty set 1, 2, 3, 1, 2, 1, 3, 2, 3, and 1, 2, 3. And there it's obvious the absolute value of A is 3, which is less than the absolute value of the power set, which is 8. Therefore, Cantor's theorem holds true. So pretty straightforward, that one. Now, just pay attention to this. This is the Barber paradox. You may or may not have seen it, but you've seen it now. So here we go. In a village, there is a barber who shaves all those and only those who do not shave themselves. Does the barber shave himself? Right, so the barber's, in this instance, it's an old paradox. The barber's shaving men, and the barber shaves all those and only those who do not shave themselves. Does the barber shave himself? That's the paradox. Now, hopefully that's sort of sinking in. So here we go. If you say yes, then he violates the rule that the barber only shaves those who do not shave themselves, and therefore he's no longer the barber. If you say no, then as the barber, he must shave himself, since he is one of those who do not shave themselves. So that's the paradox. He can't shave himself, but he has to shave himself. So the barber shaves all those and only those who do not shave themselves. So there is the barber paradox. You may think, Dr. Everett, that's great, but what's it got to do with mathematics? Glad you asked that. Let's look at Cantor's proof using the diagonal argument. Hopefully you might pick up the connection. Okay, let's construct a matrix which is Sn by Sn, where we say n is countable. So we can count up whatever Sn is and say, okay, great. So here's our matrix. So S1 is all of these zeros, ones, S3 is this one, S4 is this one, and you're really changing, as you go along each line. Okay, so we've constructed a matrix which is Sn by Sn, where we say where n is countable. Now we're going to write down the elements in the diagonal, which are highlighted in red in this instance. So they are 0, 1, 0, 0, 0, 1, 0, 1, 1, 0, 0, etc., etc. So that's just that diagonal put in line. Okay, you with me? It's good. Now we're going to invert those numbers. In other words, if it was a 1, it's going to be a 0. If it was a 0, it's going to be a 1. So now we've got this. Okay. Since this sequence exists, but it does not exist in the Sn by, move the image up here. It does not exist in the Sn by n matrix, which is countable. Therefore, the set of elements Sn by Sn is uncountable, because you've now included something which should be in that, and you've counted it, but that's uncountable. So that's Cantor's proof using the diagonal argument. It's a very simple argument. Maybe you have to dwell on it a little bit, but what he's saying is if you have this list here and you try to put it this way, it's going to be flipped, and you're going to get another sequence which doesn't exist in that. So it's becoming impossible to say that that's countable, because you've got this other one which should be in there. So here's your research for assessment test 1. Explain in detail. So this question, or very close to this question, will be in assessment test 1. And I'm not going to give an answer in any of the lectures. I'm just telling you, go and do some research. Explain in detail the connection between Cantor's theorem, the Barber paradox and Cantor's proof using the diagonal argument. So you need to do some research. It'll be worth a fair few marks. Figure that out. Figure out how you're going to answer that in an assessment test as one of the questions. Okay, on with the lecture. Okay, so this is the Schroeder-Bernstein theorem. There should be two dots above the O there. If there exists, there should be an S there. If there exists injective functions f a to b and g b to a between the sets a and b, then there exists a bijective function h from a to b. So if there exists injective functions, and remember we went back and I showed you the injective ones from a to b and b to a, then there must exist a bijective function from a to b. In other words, everything's one-to-one. It perfectly matches. Now, what we're going to dwell on with this Schroeder-Bernstein theorem is not little things. We're going to dwell on infinity. So this is where your brain starts going, you go, whoa, okay, we're thinking of infinity. So in terms of cardinality of the two sets, this classically implies that if A is less than or equal to B, so the size of A is less than or equal to the size of B, and B is less than or equal to the size of A, then the size of A must equal the size of B. So that is, if two cardinalities are less than or equal to each other, then they are equal, which obviously makes sense mathematically. Now here's an example, or here's the example. Think of a set of counting numbers, n, so you're going 0, 1, 2, 3, and off to infinity you go. Right, so you've got that in your head. You're thinking of the counting numbers. Now think of any continuous subset of n. So we want a continuous subset. So something that just keeps on going all the way, like 1, 3, 5, 7, 9, or 0, 2, 4, 6, 8, 10. One continuous subset of n. How many numbers are there in n? Answer, infinity. I already said that. The big question, let's choose the even numbers. How many numbers are there in E? So I've called it even equals 2n, where n's an element of n. How many elements are there in the even numbers? Answer, it's not half infinity, it's infinity, because you can't count that big. So this is what Schroeder-Bernstein deals with, deals a lot with infinity. So we can create an injection from n to e and from e to n. So this is my e, which is 2n, and n is the natural numbers. And so we're thus satisfying the Schroeder-Bernstein theorem. So we can create an injection from the natural numbers to e by saying, I want to get all the evens. So our injection will be 2n. And from the evens to n will be the n on 2, or 2n on 2. That gets you back to the natural numbers. So that satisfies the Schroeder-Bernstein theorem that you can go from one to the other and the other back to the first one, which satisfies that as an injection. This means, can I just make this a little bit smaller? There we go. This means that since they both have injections into each other, that there exists a bijection. In other words, they're one-to-one and onto between the set of natural numbers and the set of even natural numbers, even though they appear to be different, to have different sizes, which implies they have the same size. So this is sort of the mind-blowing stuff of, hang on, we're talking about infinity to infinity, but that's half infinity. Well, Schroeder-Bernstein theorem says that if you can have injections into each other, then there must exist a bijection which makes them one-to-one. So I'm going to leave you with that. It's really just getting your head into that space of the infinity space. And that'll do it for this week. Put up some questions there for revision. And that's it. God bless you. Get on with that research. Pray God keeps you safe. Okay. Bye.